Anyway, it's a great pleasure for me to introduce the next speaker, my former colleague Walter Wellinger. There is a wonderful quote by Wigner, where Wigner says, where Wigner says, "Give me 16 parameters and I can make an elephant. Give me 17 parameters, I can make it wiggle its tail." Walter is someone who doesn't believe that elephants should be allowed to wiggle their tails.
Thank you, Rob, and thank you for giving me an opportunity to talk in this workshop. So I realize that the title of this talk is a little bit ambiguous in the sense that is this a talk about a new internet traffic matrix problem, or is this a talk about a new twist on a matrix completion problem? I hope at the end of the talk you will realize why this ambiguity is there for some purpose. So Rob Rob Nowak in the talk in the morning showed you an example of a fruit fly, because that's the context in which he motivated his work. Here is my version of the fruit fly. It's an internet router, a very generic router. I guess everybody here knows what a router is doing in the internet. It does essentially one thing, and that is it takes a packet on the input port, looks up a table, and decides at which output port to forward this packet. It's a very simple task. And if you want to, and the routers are very good at this task, and if you want to make them do that very fast, you have to pay more, and they do it faster. But that's essentially the nature of a router, and irrespective of the speed, of the model, and of the functionality, what such a router is producing is a very natural traffic matrix, which is called the local traffic matrix. It basically gives you the traffic volume between every input port and output port. So if I would have a pointer, then I could show you where the ports are, but basically there are the input ports on the bottom and the output ports, these slabs. And you see there are only a few, not that many, and this is where you measure the volume, how much traffic goes in, how much traffic goes out, and that provides you with a very natural traffic matrix. A typical router has somewhere between 16 and a couple of hundred ports, so the traffic matrix is not all that large, but it's a very natural traffic matrix. So now it happens so that many of these routers are something called NetFlow enabled, and NetFlow is a measurement technique that actually looks at each packet and figures out where that packet, so it comes on the input port and it figures out at which output port it actually goes. So it keeps this information around, and if you have a router that is NetFlow enabled and you have some routing data available, there is absolutely no need to do any inference for this traffic matrix, because you simply measure it and compute it. Okay, very simple. Now that's one of the reasons why this type of traffic matrix, namely the local traffic matrix, hasn't attracted very much attention on the research side, because essentially for these routers that have these capabilities, there's nothing to do. A simple example is a router in Eberlin's network. Eberlin is nowadays called Internet 2, the research academic network in the US. This is a Washington router that has 16 or 15 of its interfaces are populated. And if you measure and compute the traffic matrix, this is what it looks. Very simple. This also shows one of the reasons why on the research side not that much has been done, because it makes you realize that the shape of the traffic matrix, this local traffic matrix, depends very much on how the network operator calibrated or put this router together, configure this router. So it's very much an aspect of the configuration that's human. So there's maybe not much interest in looking at lots of these local traffic matrices, because they depend very much on who configure these routers. But anyways, that's how it looks. If you look at it over time, then you see something that's very, very typical, and that is if you look at the top six, in this case, 6 traffic elements, and they follow beautiful daily cycles. So here you have 3 days and 3 weekends, so 3 work days and 3, it was a long weekend, and this is a typical picture. So there's a beautiful daily cycle for each of these traffic elements in pretty much each of the routers in the internet. So now you have this local traffic matrix, realizing that is associated with a particular router. Now you sort of step back and sort of say, this router is part of a larger network. That larger network has many routers, and then you get to a very natural next traffic matrix, and that is what's called the intra-domain traffic matrix. So here is this Abilene network, very simple network in the US, about 11, 12 nodes. You see the Washington node sitting there on the right-hand side, which I just showed you, and then there are all these other ones. And you can now ask the question is, how much traffic that comes into, let's say, New York goes out in Sunnyvale, or something like that. And so that gives rise to another natural traffic matrix. And that's just traffic volume per time unit, and the time unit can be pretty much anything, 5 minutes, 1 hour, 1 day, between egress or ingress routers or POPs. For the purpose of this talk, don't worry about what POPs are, it's just routers. And so this is now another natural traffic matrix, and in terms of size, we talk about large networks have about a couple of thousands of routers. So this is slightly bigger than the local traffic matrix, and so this is a little bit more interesting to look at. It's also a little bit more interesting to look at because the data that are network-wide readily available are typically have not been on this NetFlow nature, but more of this SNMP nature, which is simple network measurement protocol, which essentially only measures, so each router on each port only counts each packet or byte that flows into that port. It doesn't distinguish between the packets that flows in and goes to a particular destination. Okay, so it just counts. And so these SNMP data now are readily available network-wide at every router, at every port. Now, so if you have this, then you try to see what can you do with this sort of data in terms of inferring the intra-domain traffic matrix. And essentially what you have to do is you have to solve this equation. And for the purpose of this talk, just think of this traffic matrix X that we are interested in as a tall vector where you stack all the columns of your matrix on top of one another. And then Y is the link measurement data, and A is the routing matrix, which basically says which link is associated with each route, or which route uses which links. Okay. And so in real networks, this is a massively under-constrained problem, and this has given rise in the last 10 years to significant research in the area of traffic matrix inference. And I just give two references of pieces of work that your colleagues of mine have been involved with, and they had significant impact on how traffic matrix inference has been done and used in practice in the last 5-10 years. So in terms of applications of this traffic matrix, these are very nice examples of relevant research that has impact on network operations, whether it is network engineering or traffic engineering, in the sense that if you know the traffic matrix, you play with situations where one link goes down, what do you do in terms of rerouting? All that you can play with a given traffic matrix. Anomaly detection can be done. And then, so in general, just enormously useful for daily network operations. And it's sort of amazing to realize that up to 1999, 2000, these traffic matrices have not been available for network operations. And so a textbook example of how theory impacts practice. Now, one thing changed now in the last couple of years, and that is, I said all this work has been based on this fact that we only have this SNMP data available network-wide. In the last couple of years, we got to the stage where every router in our network was enabled with NetFlow. So suddenly, again, there is no more need to do inference. We measure, collect the data, compute the traffic matrix, no more inference necessary. So in some sense, all this beautiful research that has been happening in the last 10 years suddenly becomes irrelevant, okay, for this purpose. And again, I mean, there is sort of a lesson to be learned from this, but so this is exactly what happened. So in the Ebeling context, all these routers are NetFlow enabled. You have these 11 or 12 nodes. The traffic matrix that you get for one particular day looks like this, and this is a reasonably typical traffic matrix in the sense that most elements are small. There are a few large ones, and the large ones are typically the diagonal elements. And again, even on the network-wide side, the daily cycle is always there. This is a typical characteristic of internet traffic, irrespective of where you look. So even so now, in the last couple of years, the interest in traffic matrix research has sort of decreased significantly. There are still lots of open and interesting problems that are quite challenging. I just list a couple of them here. And one of the biggest challenging problems that remains is how do we realistically generate traffic matrices? Because the research community still has the disadvantage over us who work for a network operator. They don't have a realistic traffic matrix to use in their research. So this question of how do we realistically, how do we generate a realistic traffic matrix remains pretty much completely unknown. And it points to one of these important ingredients that's needed in order to do this synthesis of traffic matrices. What aspects of the underlying network is important to generate realistic traffic matrix? In other words, what sort of fingerprints of the underlying network can you see in a traffic matrix? We don't know that. Another thing that we don't know is really what are the root causes of observed phenomena in measured traffic matrices. So lots of these traffic matrices have been shown to have low rank, or if they don't have very low rank, then they have some rank. So instead of 3 or 4, they may have rank 8, 9, or 10. And then the reason we ask the question, what's the difference between networks that have very small rank versus medium-sized rank? And then some of the traffic matrices also exhibit quite a bit of sparsity. All this you expect to have root causes that one can explain in the network context. This has not been done. And then a last question that sort of sits there, and again, given the net flow availability of data, it's not anymore that important, but you could imagine 5 years ago this would have been an important question, namely, if you are asked in a large-scale network, where do you put your monitors so that you get the best possible measurements for your particular problem? This question hasn't been addressed either, and remains open. So why is there this interest for large intra-domain traffic matrices? There's just a list of questions that you can ask once you have them. So network operators want to know, for example, how much of the traffic that enters my network in New York, for example, is destined to Atlanta or any other pair of cities. Another question that now can be addressed is, much of the traffic that we see on our network is due to content distribution networks. How much of the traffic is due to content distribution networks? That's something that people on the networking side, on the operator side, even on the content distribution side are interested to answer. Yeah. I put this question in there not because my colleague will talk about Netflix later on today and at the dinner, but because this is currently one of the most intriguing problems and questions that we need to understand, because within the last year, our network has seen Netflix traffic grow from single-digit numbers all the way to 30 or more %. So within 1 year, one network contributes almost a third of the traffic on our network. Is responsible for 1/3 of the network on our network. So observing such phenomena Once you have the traffic matrix, you can do it. Without traffic matrix, you don't know. And then, of course, every network wants to know how much total traffic does our network carry on a daily basis. And with the traffic matrix, again, you can quickly and automatically come up with the right numbers on a continuous basis. So now, here are a couple of questions that I cannot answer knowing the intra-domain traffic matrix. So I cannot answer the question, how much traffic do Sprint and Verizon exchange with one another? Because I don't have that information in the intra-domain traffic matrix. I don't know how much traffic Verizon dumps onto, Netflix dumps onto Verizon. I have no idea. What are the networks that exchange most traffic with Google? Again, these questions I cannot answer with intra-domain, because intra-domain means I only know about my domain and I don't know anything about else. How much does Facebook's traffic increase on a monthly basis? Or this question, which you would expect everybody sort of will know, how much traffic does the internet carry on a daily basis? This is a question that really nobody can give you an answer except some estimates. But how these estimates have been obtained is always a big question mark. So here is a set of questions that I cannot answer with intra-domain traffic matrix information, but I could answer if I had a different traffic matrix. And that traffic matrix I get if I step back yet one more step and sort of say, so I started out with individual routers and view them in the context of an individual network that had many routers. Now I step one step further back and view that network in the context of the larger internet, which you have to think about is as a network of networks. So if you think of the internet as a network of networks, we also call these individual networks autonomous systems. Then we talk about a system that has about 30 or 40,000 elements. And the nice thing about the ongoing research that's happening on the internet side is that we are getting a clearer and clearer picture over time about the connectivity of these elements that make up the internet as a network of networks. So who is exchanging outing information with whom? And once they exchange outing information, the likelihood that they actually will exchange actual traffic is very high. But it doesn't necessarily mean that they do. And so this gives rise then to this inter-domain traffic matrix, which is simply giving you the traffic volumes between individual domains. And unfortunately, what we know about this stuff is we don't know absolutely nothing. This is an object that it looks so natural, but it's incredibly hard to get any information out to understand what this object is all about. Now, let me just point out a couple of things that, in terms of, it's completely unknown. There are a few things that we can say. So, in 2010, the internet is just, there has been some estimates that the internet carried some 20 exabytes of traffic per month. Around the same time, one network, AT&T, carried some 20 petabytes per month, per day. Okay? And so you roughly have about 20 networks that are like AT&T making up part of the internet. So that tells you already something in terms of this inter-domain traffic matrix is really highly structured in the sense that there are a bunch of networks that are responsible for most of the traffic. Now there's a little twist to this problem in the sense that these large networks do not have just one network that they use to run their business, but typically they have lots of networks. And the question is really, which one of these networks do you have to count? For example, in AT&T's case, how many of these individual networks make up AT&T's overall network structure? And that's ongoing research. So that's something that can be done, but it's not easy, but it will be done. and we will know about this stuff. We will have a reasonable good mapping between networks and organizations. And then you can ask the question, how much traffic does AT&T as an organization exchange with Verizon as an organization, for example? So it's slightly more complicated than it sounds, but anyway, so what this slide illustrates is this interdomain traffic matrix is something that's highly structured. So it's certainly not something that has no structure. So here we are in terms of then formulating something that we may want to call a traffic matrix completion problem. So we know we can. So if you come to me and sort of say, what can you tell me about this traffic matrix, this interdomain traffic matrix? I can give you about 1% of these traffic elements. And because I know that which networks are roughly involved, and I can tell you more or less, or give you a reasonable estimate about the size of these different traffic elements, these 1%. Then you have to sort of take a leap of faith and sort of say, okay, let's assume interdomain traffic matrices have low rank. Nobody knows whether that's true, just let's assume. And then there you're sitting there and sort of say, doesn't that look like sort of a relative non-standard matrix completion problem in the sense that it violates any assumptions that most algorithms assume, in the sense that these 1% or these few percent of elements are not random, they are highly structured. I have no idea whether this low rank assumption is true. But my perspective here is now, look, I'm not an expert on on matrix completion. All of you know much more than I. And maybe there is somebody out there who will actually be courageous enough and use a particular algorithm and run it. What I'm interested in is I want to be ready if somebody comes and gives me a solution to this matrix completion problem. I want to be ready to say, this is a good solution or this is a lousy solution. And how do I do this? So this points out one of these nice things that come with sort of internet-related research. I can start now thinking about what sort of measurements could I take in the network that have never been used in this context of matrix completion here, that I could use to validate whether your matrix that you generated is good or bad. So here is a prime candidate for such measurements that are being done as we speak. So there is an infrastructure called Internet Exchange Points. So the business model of it, so these are physical third-party facilities, and their business model is you become a member, you pay a little price. Once you're a member, you are allowed to connect to any other members of this IXP. And essentially, you can then exchange traffic for free. So economically, it makes lots of sense because it's a cheap way to connect to other networks, in particular in view of the alternative where you have to ship the traffic upstream to your provider, and that always costs money. So here you have an opportunity to cheaply ship traffic to the places that you may want to have as your peers. And so in this particular context, I put in a couple of these links that sort of say, here you may have a situation where this content provider, instead of sending the traffic upstream and then downstream to the particular AS1, AS2, and AS5, they just connect directly there, and the content provider doesn't have to pay a single dollar to the upstream provider. So the economics makes lots of sense, and so the question now is, what do we know about this infrastructure of internet exchange points? So we have a couple of, about 300 such internet exchange points in the internet. And they are estimated to be responsible for about 10 or 20% of the traffic. So I have 50, 60% of these tier ones, 10 or 20% of the traffic of these IXPs, so I'm already up there at 80 or 90%. These 300 IXPs involve about 4,000 ASs. So it's 4,000 ASs that in these various IXPs are members and connect with other members. Another nice thing about this stuff from a traffic perspective is that these IXPs publish their hourly, daily traffic volume, aggregated. And then what we are currently working on is we are getting a better and better picture about which networks are connecting with which other networks at which IXPs. So we get a picture of these peering matrices, and then the question is, once we have the peering matrices, can we get the traffic matrices for these IXPs? So the new twist in this context is, how do we infer the local traffic matrix that are IXPs, and then, can we actually go about measuring them? Because once we can measure them, then we have, again, a number of elements in this traffic matrix, in this interdomain traffic matrix, that we can associate values with. We know which one are positive, how much traffic they carry, and so we can start, increasing the accuracy of any sort of solution that comes along. So the idea here is really, if we start with the formulation that we have today that only takes into account this very structured way determined by the presence of these large tier 1 network service providers, and you solve the problem and it doesn't really provide a very good solution to what I'm interested in, then you would come and start to incorporate this next level of information that I was able to provide, namely these measurements that come from the IXPs. And most likely, if you start to incorporate those measurements, your solution to the matrix completion problem will be much, much better. How much better, that still remains to be seen, but at least it's a nice way of thinking about how you can make progress along these lines. And so you start to repeat this process until you sort of are satisfied that the traffic this traffic completion, the solution to the traffic completion problem that you give me satisfies, is consistent with most of the measurements that I potentially can take and check whether your traffic matrix is a good one. Okay, so I showed you that in this context of the internet, there are a number of very, very different types of traffic matrices that appear in a very natural way, and they are all sort of, fit together in very interesting, intriguing ways. The router level, the local traffic matrix fits into the intradomain traffic matrix, and the intradomain is one piece of the large intradomain traffic matrix. And so this is it's a nice area where research has made quite a big of impact so far, at least along the lines of intradomain traffic. What it's not yet done is the interdomain traffic. So on the intradomain aspect, it has been a beautiful example of how new research can provide extremely practical benefits to network operators. Unfortunately, the changes that have happened in the network have made that research irrelevant now. There is another aspect to this notion of trying to understand traffic matrices at different layers in the internet, and that's just pointed out here in the sense that as far as individual networks are concerned, the knowledge of the intradomain traffic matrix is a basic ingredient for a first principle approach to understanding an AS level, router level topology. And in that sense, it's a very, very different approach to the very popular network science approach that tries to say you don't need to know these details to understand this type of networks. And it's a nice reminder, this change from data that were not available and then suddenly overnight, more or less overnight, became available, is a nice reminder that these things do change in the internet, and you have to account for those changes when you look at your research. So lastly, so as far as the interdomain research is concerned, again, the practical value would be enormous in terms of you could answer all of these questions that I posed a while ago. It does provide a new twist to the generic matrix completion problem formulation in the sense that being able to be ready to validate a given solution is something that is certainly necessary at this stage, because most likely any generic solution will not be terribly good. And then we have a parallel observation here as far as the interdomain traffic matrix is concerned. Again, it will be a critical ingredient to do any study of a first principle approach to understanding the internet at the level of individual networks. And so, there is tremendous potential there. What I said there at the end, I mean, this still needs to be done, and how long it will take, that's a big open question. But I mean, it certainly it won't be done within a very short period of time. It will be a big research problem. Okay, thank you.
Whilst we're setting up the next question, we maybe have time for a question if there is one in the audience. I'm wondering actually why, I mean, I remember from my time at AT&T that it was very hard to get Cisco to consistently provide net flow data. What changed their mind?
Money. Yeah. No, I mean, you're right. I mean, there was always the belief that every router will sooner or later have net flow.
Yeah.
But, 2005 came, it still wasn't the case. 2008 was there, it was still not the case. So the fact that we had solutions to do inference without it was very good. But then suddenly it was possible.
Do you think the fact that you produced solutions made it cheaper in the end? I don't know.
I don't know.
Anyway, let's thank